So now we're going to cover the second chapter on aromatic compounds. This is aromatic substitution. So the last chapter, chapter 17, was about the aromatic compounds, their characteristics, and the reactions that could be done on the aromatic compounds themselves. This chapter is going to discuss functionalizing those aromatic compounds. So now we're going to be adding functional groups to the aromatic compounds, how to do that and how that influences the molecule once they're attached to the molecule, once those attachments are made. So this time in this chapter, it's a rather long chapter, we're going to have 4 separate lectures. So this lecture is the first lecture, and it's going to cover sections 1 through 5 in chapter 18. So you can see this, Introduction to Electrophilic Aromatic Substitution. There's going to be a lot of these different reactions. They're going to all follow the same mechanism. So it's going to be very important. It's going to be essential that you learn that mechanism because it's going to apply to all of these reactions. That's how you can simplify it, is by recognizing that all these different reactions have the same mechanism. If you can recognize the commonalities, it will make it so much easier. So that's what I'll emphasize. Then we'll cover an additional one, and then we will start to analyze the characteristics of these different reactions. So let's get started and cover these different reactions initially. So we already know that it's possible to add bromine across a pi bond, and that bromine does not simply add to benzene in the same way that it will add across the pi bond in cyclohexane. However, it is possible to brominate benzene if you add a catalyst. And one of the catalysts that works is a little bit of iron. So this iron, in the presence of bromine, becomes ferrous bromide, FeBr3. And so that is the catalyst that catalyzes this reaction. And you'll see that in just a moment. There are many different electrophilic aromatic substitution reactions. These are the ones that we will cover, and these all go by the same mechanism. Notice that here are the functional groups that are being added. And so one of the things that you'll have to recognize is which reagents are required. You'll have to learn the reagent to affect this reaction, the reagent here, etc. And you will have to learn the electrophile that is provided by that reagent. And so let's start looking at some of these reactions. So here, this is the nucleophile in bromination. This is the electron-rich center, the pi bond. This is delta plus, delta minus, the bromine electron density in the molecule becomes polarized in the presence of this electron-rich center. And so a Lewis acid catalyst is needed to make this electrophile more reactive. So what it does is it actually polarizes this bond even more. And so, as I said, when you put iron in the presence of bromine, you form iron bromide. And this is the Lewis acid catalyst. So here is how the molecular bromine becomes either polarized or furnishes a bromine cation. So you have the molecular bromine. Here's a pair of electrons which attacks the iron of the iron tribromide. And now you can see in some cases it's enough just to polarize this bromine. Here it's depicted as the pair of electrons in the molecular bromine actually moves on to bromine, and then iron is bearing a positive charge, and iron is bearing a negative charge, bromine is bearing a positive charge, and so this is now a salt. So this is obviously a more potent electrophile than when you just have molecular bromine polarized by being in the presence of a pi bond. So this makes the bromine even more electron poor. This is much more reactive, and so it's reactive enough to actually react with the pi electrons in benzene, and that's what we're going to see here. So the first step, now you can see here, this is not depicted as being a salt. So here it is depicted as still being attached, and the molecular bromine is just polarized a lot more. The pair of electrons in the benzene ring attacks bromine, and this pair of electrons that is bonding the two bromine atoms together moves on to this bromine, which is bearing a positive charge. And so now you have this counter ion, the anion that is liberated here shows up again later on over here. This is generated in that step. The bromine becomes attached, so you have a new bond formed, and this reaction goes rapidly. So you have a cation. This cation is called a sigma complex, and it has 3 different resonance structures, which you can see here. So here you have a positive charge generated up here when that pair of electrons moves out and attacks bromine. You have a cation, and so the positive charge moves around the ring. As you see, the whole thing is called a sigma complex, not just that one resonance structure. And so now you can see that you have one of these carbons is bearing 2 substituents. It's bearing the new functional group, and it's bearing the same hydrogen that it was bearing originally. And so the goal is going to be to get rid of that proton, because you need to regenerate the aromaticity to make this into a stable molecule. Regenerate the aromaticity by the pair of electrons in the CH bond moving back down to form the 6 pi electron cloud. So this pair of electrons moves back down, it satisfies the positive charge, and so now the proton is removed. It goes off as HBr, up here you can see, and you have the iron tribromide, and now bromine is attached to the ring. So overall, the reaction is to replace the hydrogen with the bromine. In each one of these reactions, you're going to be replacing hydrogen with something. And it's going to have many steps in common. The steps it will have in common are that you're going to have a nucleophile, okay? The pair of electrons in the benzene ring will attack the nucleophile. You will have to be able to know what the nucleophile is in each case, because it's going to be different in each reaction. Okay, the nucleophile will provide the substituent that you wind up with. So this nucleophile, this electrophile is going to be providing the substituent that you find in the product. So this electrophile is going to have to be formed by the reagents. So you'll have to know the reagents, and you'll have to know the electrophile that the set of reagents provides, and you'll have to know the new substituent that comes about as a result. So that's going to form a set for each one of these reactions. You'll need to learn that. You'll need to learn the reagents and the electrophile and the new functional group. Another thing that's common in each of these reactions is there will be a sigma complex. Whatever it is that the electrophile provides, that will be attached to the benzene ring in the sigma complex. In this case, it's a bromo functionality. That is what the substituent is. That is what this electrophile is providing. It's providing bromine. And so that is what you see in the sigma complex. This will change for every one of those reactions, but you will always have this. Sometimes it may have 4 different resonance structures, sometimes only 3. In this case, it's 3, but it doesn't matter. This is called a sigma complex. So the sigma complex is going to be positively charged. It's going to be a cation. A pair of electrons is used to pick up the functional group that you wind up seeing in the product. And so that pair of electrons, when it comes out of the ring, it generates a positive charge. And that positive charge can go around the ring in different resonance structures. All of these resonance structures combined are called the sigma complex. And so then the last step is you need to lose a proton. You will lose the proton that is attached to the same carbon as the incoming functional group. Here it's this one. And the pair of electrons will move back into the ring, satisfy the positive charge, and regenerate the aromaticity. So that is a step that is always going to be in common in all of these reactions. And so then you will have the new functional group attached to the benzene ring. So those are the steps that are in common. So you will see the mechanisms, and I might go through them a little bit faster because they're going to look just like this. Once you've seen the first one, you've seen all of them. There will be a few little differences, but the vast majority, they will be the same. So here is an energy diagram, and you can see the reagents start out, they go over this energy hill, and then they form this cation, which is a reactive intermediate. It is at an energy minimum. This is the sigma complex with the different resonance structures. And then it goes on over the next energy hill and down and forms the substitution product. Now notice that you could add another bromine substituent, but then you would generate a higher energy product. Let's go back up here. So see, you could have bromine come in and attack, but that would generate a higher energy product, and it would not regenerate the aromaticity. And so you have the aromaticity regenerated, the proton is lost, and you have the substitution product down here at a very low energy existing in this energy weld. And so the addition would be going uphill energetically. Instead, you go downhill energetically to the substitution. Aluminum tribromide could be used instead of the iron tribromide. The reaction, the mechanism would be exactly the same, except you would have aluminum and aluminum and aluminum. And otherwise, it would be exactly the same. Now, you can also have chlorination using aluminum trichloride with chlorine. And so the mechanism is exactly the same. The steps are exactly the same, except instead of adding a bromo substituent, you're adding a chloro substituent. And so I'm not going to, I don't think the mechanism is even in my slide deck. Fluorination is too violent. It's too unpredictable. And iodination is just too slow of the reaction. It just doesn't take place. So it's not practical to use it. No, here is chlorination. You see it is exactly the same. Instead of bromine, 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 you have chlorine in all of these places. And the arrows are all the same. The sigma complex is the same. This is the same as you saw in the mechanism with bromination. So here is the general mechanism. You're going to have an electrophile. The identity of this electrophile will depend upon the reagents that are used. You'll have to know the different electrophiles. You'll have to know the different reagents that provide those different electrophiles. And you'll have to know exactly the substituent that the electrophile provides, because that substituent is what you see in the product. So those three things you'll have to be able to recognize and predict. You'll have to be able to predict the electrophile from the set of reagents, and you'll have to be able to predict the functional group that is attached from the electrophile or from the set of reagents. So you can see the general mechanism. The pair of electrons attacks the electrophile. Then the positive charge rotates around the ring and in different resonance structures. This is called a sigma complex. The sigma complex is deprotonated using a base. It can often be something that is given off here in the nucleophilic attack, as in the case of bromination. So this deprotonates the pair of electrons in the carbon-hydrogen bond, move in, form the new pi bond, and satisfying the positive charge. So you have to remember that wherever the electrophile attaches, that carbon atom is the one that's going to be deprotonated. This carbon has 4 bonds. In the product, it's going to need to wind up with just 3 different attachments to different atoms. And so here it's attached to 4 different atoms. It's going to have to lose the proton. This is the carbon that's going to have to lose the proton. You can't get mixed up and start thinking that it's this hydrogen or that one or one of the others. It's always the CH bond on the carbon bearing the incoming group. So sulfonation, SO3 is the electrophile, and sulfuric acid is the catalyst. So it's the sulfuric acid that provides the SO3, and so fuming sulfuric acid is used to sulfonate the benzene ring. Here you can see that the oxygens are all bearing the bulk of the electron density, so they're all colored in red in this electrostatic potential diagram. SO3 is a strong electrophile. The sulfur atom has a significant positive charge because of the inefficient pi overlap. So the p orbital on sulfur is a 3p orbital. This is a 2p orbital. And so there's not very good overlap here. And so that makes the sulfur-oxygen pi bond somewhat weak, and this will have a lot of single bond character. So here, this is the sulfonation. So this is the electrophile that's provided. Pair of electrons moves in, forms a bond to sulfur. This is the carbon that is now bonded to 4 different atoms. This is the carbon that's going to have to be deprotonated. Here is the sigma complex, just as always. The positive charge moves around the ring, as you've seen before. Now, this proton has to be deprotonated from that carbon atom that is attached to 4 different atoms. The pair of electrons in the CH bond moves back in to satisfy the positive charge and restore the aromaticity. Then the sulfonate groups picks up a proton from the protonated water, the oxonium ion, which pull the proton off of the sigma complex, and so that gives you the functionalized benzene ring. Sulfonation is sensitive to reagent concentration. It's a reversible process. So in other words, you can use concentrated fuming sulfuric acid. So this is going to have some heat, and this will sulfonate the benzene ring. So that means that if you dilute this, just add water, you can remove this sulfonate group and revert back to benzene. And so this becomes useful if you have to put sulfonate on as, say, a blocking group, and then remove the sulfonate on down the line to remove the blocking group. So this is useful, being able to reverse the process. Now, nitration occurs by using nitric acid, and it's the source of the electrophile. Sulfuric acid is provided as the acid catalyst. The nitronium ion is the electrophile. So nitric acid is providing the nitronium ion. So you have to be able to get the nitronium ion out of the nitric acid. So the first step that happens is the nitric acid is protonated. So here we have nitric acid. It's protonated by sulfuric acid. So now you have the oxonium ion here. And so you're going to lose water. And when that happens, you get the nitronium ion. This is the electrophile. So, for example, you're going to have to know that if you have nitric acid and sulfuric acid, you're going to generate the nitronium ion. That is one of the pieces of information you'll have to know for this reaction. And you'll have to know the analogous reagents that generate the electrophile in every other one of these reactions. So here we have the electrophile. You have nucleophilic attack on the electrophile. A pair of electrons attacks the nitrogen bearing the positive charge. You have the carbon-nitrogen bond formed. Now you can see this carbon is bonded to 4 different atoms. This proton is the one that's going to have to be lost. And so this is the sigma complex that is generated, again, as in all of the other electrophilic aromatic substitution reactions. The positive charge migrates around the ring. Then the sigma complex is deprotonated using water. This water was generated when the nitric acid lost water. So now the water plucks off a proton, the pair of electrons moves back in to the ring, regenerating aromaticity and satisfying the positive charge. So here the nitro is the group that was attached. So you'll have to be able to remember what is the group that's attached, what is the electrophile, and what are the reagents that provided that electrophile. A nitro group can be reduced to form an amine using iron or zinc and hydrochloric acid, and then in the second step, you neutralize the product. Otherwise, this is going to be present as the amino group. Combining the reactions gives you a way to actually put an amino group on a benzene ring. So first you nitrate the benzene ring, and then using these two steps up here, you reduce the nitro group to the amino group. Alkylation occurs by using an alkyl halide. Here we have the secondary alkyl halide. This is the electrophile. It has to be activated by the aluminum trichloride or some other Lewis acid catalyst. And then the alkyl group will simply become attached to the benzene ring. And so the way that the electrophile is generated is the pair of electrons on chlorine becomes attached to aluminum. So aluminum is bearing a negative charge, chlorine is bearing a positive charge because the pair of electrons was donated to aluminum. And then the pair of electrons in the carbon-chlorine bond moves on to chlorine to satisfy the positive charge, and it generates a positive charge on carbon. So here, this has generated the carbocation. Now we have the alkylation mechanism. This is the electrophile, and it goes through the same steps that you've seen earlier. The pair of electrons moves in to attack the positive charge. The sigma complex is generated. The positive charge moves around the ring, getting all these different resonance structures. This carbon is the one that's attached to 4 different atoms. This carbon is the one that's going to have to lose the proton. And so chloride comes in, plucks off the proton. The pair of electrons in the carbon-hydrogen bond moves in to satisfy the positive charge and regenerate the aromaticity. So simple primary halides can be used effectively, but the primary carbocation is not going to be stable, and so here it's assumed that the electrophile is this complex, and so this is the electrophile, not merely the carbocation in that case. But most of the primary alkyl halides are susceptible to rearrangement, and so you may not actually have the primary alkyl group as the substituent. You may have the secondary alkyl group because the primary carbocation that is formed rearranges to the secondary carbocation. And so this is evidence of that taking place, the fact that you have the primary alkyl group as 35% of the product and the secondary alkyl group is 65% of the product. Okay, 3 other limitations to Friedel-Crafts alkylation. The halide leaving group must be attached to an sp2 hybridized carbon because the aluminum trichloride will not catalyze a reaction with this vinyl chloride. And it will not catalyze the reaction to using chlorobenzene. So in each case here, the chlorine is attached to an sp2 hybridized carbon, chlorine is attached to an sp2 hybridized carbon, and in each case, there is no reaction observed. Polyalkylation can result because once an alkyl group is attached to the benzene ring, that activates the ring towards additional substitution. And so once the first alkyl group is put on, the benzene ring becomes even more reactive. And so you may see additional alkylation. And some substituted aromatic rings, like nitrobenzene, are just too deactivated, and so they just don't react. The pair of electrons simply is not free enough to be able to attack the electrophile. So here the problem is that the ring becomes too activated, and after the first substituent is attached, because the substituents will be attached in a stepwise fashion. First one goes on, then the second one goes on. And sometimes you can't control, even if you don't want the second one to go on, sometimes you just can't control it. You don't get what you want. And so here the benzene ring is too activated. Down here, the benzene ring is deactivated, and so there's no reaction. So this is a good stopping point, because we have covered some of the substitution reactions and the mechanisms for those substitution reactions. And so in the next lecture, we will look at additional substitution reactions, which have mechanisms analogous to these, and we'll look at what happens when you need to put a second substituent onto the ring and get multifunctional compounds.